All right, so let's take a look at part 3. The main topic here is simplification, which we've already done. But I'm going to try and, again, reinforce some of these things for you guys in this. Okay, so no new content in this part, okay? This part is about reinforcement of stuff that we already have, as well as formalizing some of these techniques that we've been talking about informally for a while now, okay? So there is one new thing in here in terms of sort of strategies that I'm trying to put forward to you. Okay, so here's one thing that kind of is covered in your general math curriculum. It's not a specific point, but one of the things that they want you to be able to do after coming out of grade 9 math is be able to easily go between 3 different styles of math demonstration. With this I mean you can write out algebra using symbols. Symbols like variables, symbols like adding and subtracting, multiplication and division. That's symbolic math. Shh. As well, you should be able to model this. The current model that in this algebra unit that we are incorporating is the algebra tile model, okay? Whether you like it or not, it is part of your content. And then finally, the final piece is to express this in a verbal sense. Now, this doesn't mean you have to actually say it out loud. There's no one on the test that's going to say in your final exam, please tell me what this says, and you have to speak it. But what that implies with the verbal is that, yes, word problems are a part of this content. Okay, being able to read it and then turn it into an algebraic expression is for sure part of this. And for some students, the word problems throw them off. Okay? But honestly, that's probably one of the most important things you need to know in math is how to take that stuff where you're working with just x and y and actually apply it to something real, something tangible. It's something that actually makes sense. Okay? Here's stuff you should know. Okay? I think most of you do. That when we speak of multiplication, we're also speaking of the word product. Product and multiplication mean the same thing. You also know that there are now a couple different symbols that you can use for multiplication. We're moving away from using that x. I saw that still on a few of your quizzes and a few of your assignments that you're still using an x to mean multiplication. Please don't, okay? This symbol is now out of date. You don't use it anymore, okay? If we want to represent x times y, we can just put it as xy. Okay? We know that means x times y. Okay? Addition, subtraction. Watch out for questions that say things like 1 more than or 1 or 2 less than. They're talking about addition and subtraction. Opposite means reversing the sign, right? Right? So again, when you see that, understand that that's what's going on. We are changing the sign. And then the word sum and difference also can mean addition or subtraction, right? So watch out for those slight differences in the way a question is worded. Because remember, a big part of understanding the question is knowing what it's talking about. And one of the words you should know is the word equivalent. Equivalent essentially means equal, okay? But in the realm of algebra, equivalent has kind of a different context to it. Okay, now in these two expressions, actually, pardon me, these two equations, 4x plus 2 equals 6 and 2x plus 1 equals 3, those two are equivalent equations because in both equations, x will equal 1 if you solved it. Okay? So in both of these, even though they look like two different questions, they are essentially equivalent expressions because of the fact that in both ones, x equals 1. Okay? So again, watch out for that word equivalent. It essentially means equal, but once we start to add algebra to it, it gets a little more complicated. So let's do a little match game. Okay? Which is the equivalent for each of these? Let's start with one of the easy ones. In which one is x equal to 6? On this side, which one is it lining up with?
X plus 2.
That one? Okay. What about 2x equals 6? Which one would you say it matches up with? It's a little harder, doesn't it? Okay? Or x plus 1 equals 4. Do you see one that would equivalent to? Tynan.
2x plus 6 is the third one down
This one is equivalent to x plus 1 equals 4?
No, 2x plus 6.
Oh, 2x equals 6? You say those two are equivalent? Why?
Because 2x equals 6, 2x is 6. If you carry that over to the other question, 2x is 6.
Okay, but hang on. What's x in this equivalent? In this, if we were to solve it, 3. Would 3 work here? Yeah. So you're right. It's equivalent. Okay. So you can see kind of it can get more complicated. So let's play the match game. That one and that one. Okay. In this case, it's because of the fact that we're just kind of dealing with the fraction part, and we can kind of rewrite the fraction in a different way. Okay. That one, you guys nailed that one. Matches up with the first one. That one, yes. Wait a minute. Can that one be equivalent?
Yeah, it can.
Yeah, because it's also equivalent, right? In this case, 3 divided by 3 is 1, so yes, it works. But look at the next one. It also is equivalent. So really, these two could have matched up with these two in either direction, okay? And then we have one left there that one's going to match up there, okay? Watch out for those. There was a question like that, I think, on the quiz, and I've seen these types of questions about equivalent on final exams. I think in a lot of ways they can be tricky questions. I'm not a big fan, but I would do you guys a disservice not to show you these types of questions. Okay, so now let's work through an algebra problem, okay? Remember, the two things that are super important is what are the words being used, know the language of algebra, and develop a reliable method. Do you have to use my method? No. Can you adapt my method? Yes. As long as you're using a method to get from question to answer, and in some way you're showing work in between, then you got it, okay? For some of you, you may want to just totally use my methods, because that's a good way to work it out for you. For others, you may sort of adapt my method. Go, well, I'm going to use a little bit of what Wok said, but I don't want to write all those steps. I'm going to kind of make shortcuts here and there. And for others, you might change to a different thing. I worry, though, sometimes that if I show you 20 different ways to solve a problem, I'm just making things more confusing, okay? So if you're that kind of student, and kind of yesterday we talked about learning styles, where you need to be shown, just I don't need 20 ways, just show me one way to get her done, then I'm going to show you one way to get her done, okay? And that's the one you're going to fit, okay? Okay, here's some vocabulary you should be familiar with. I don't have definitions for these, but these are words that should be at least words you've seen before in this unit. And if these are words you don't know, you probably should know before the next practice test. Like if you don't know what a coefficient is, you should probably learn that. If you don't know what a polynomial is, you should probably know that, okay? But these are words we have been talking about. So I hope they're at least starting to make a little more sense when you see them. Because these are the words that are going to be on your final exam. They're the words that are going to be on your unit test. And if you can't get past the word, there's no way you're going to solve it because you can't even get past the wording of the question. So at least start with that. Start with knowing the words. Now, you got the words. We're moving on. I've presented two big ways to solve algebra problems so far. And this has nothing to do with BEDMAS. That was before algebra. I've presented two methods. One I called the cake method, where that's for simplifying and coming up with terms. And the other one, which I never gave a name to, I now will, is called the inverse operations method. Okay? You might even want to shorten it to the IO method, right? Solving equations using a method. And again, you may vary these a little bit, okay? But they give you a recipe for success. So let's try them out. Cake method, okay? Here's the way I've formally explained it to you. Step 1. Imagine the entire expression as a whole, as a cake. It's a whole thing. Step 2. Divide or cut the cake by placing lines before each sign, cutting it up. Your signs are going to be the positives and negatives. Step 3. You now can count how many terms you have based on how many pieces of the cake. So I have 4 terms. And then step 4, I can look for terms that are alike. And again, you need to know what that means, but alike terms means terms that have the same variables. And I can combine them. 5x minus 2x, 3x. 5 minus 3, 2. Therefore, I get 3x plus 2. Okay? It's a simple method, but it gets you through a lot of problems in terms of simplifying. That's the cake method. Now, that was the easier one. The cake method can be incorporated into the next method, the inverse operations method. This one's a little harder, but let's get going on it. For a week now, we've been talking about it. Here it is in formal terms. Step 1, remove any brackets. Good news, that didn't apply. Okay? Step 2, combine like terms. Here we use the cake method. When we're dealing with an equation, we have a cake on one side and a cake on the other, so we have to divide each side equally up and then start simplifying it. So we're rewriting this in simpler form. That's done. Step 2 is done. We've combined the terms. Step 3, all variable terms are on the left-hand side. So any variables over here, I get rid of them. I can use the inverse operation. In other words, to get rid of a negative x, I can add x. Or, for some of you, you thought of it as, let's just move it over there and change signs. That works too. Okay? So now I have the add 3x, so I get 15 minus 5 equals 10. Move on to step 4. All constants should be on the right-hand side. So I have this constant, negative 5. I get rid of it with positive 5, but I have to do the same to the other side, and I'm here. Okay? Moving on to step 5. Repeat step 2. Combine like terms if necessary. It's not necessary. There's nothing left to combine here. Okay? On bigger problems, yes, that might be the case. But in this one, nothing to worry about. I don't need to repeat step 2. Step 6, isolate the variable. I isolate it by either dividing by the coefficient or multiplying by the coefficient. More commonly, you're going to do dividing. Okay? And I'm left with x equals 15 divided by 15, 1. And I'm done. You've seen it from me now for a week. Now you have it in formal written terms. You have the steps. You have even an animation that goes with it. This will be part of today's notes. So it's in your notes. It'll also be part of your review at the end. Okay? Okay, one thing that a few students asked me about that I put in here extra, I did talk about it in part 1, but I want to be formal about it. These algebra tiles that we've been talking about as tools for solution, I know they're controversial. Some of you are not a fan, but they're definitely part of something you have to know. So here's what they are again. Okay? A filled-in tile represents a 1. A small little filled-in tile is a 1. A non-filled-in tile is a negative 1. A filled-in long tile represents an x. A not filled-in long tile represents a negative x. But here's the two tiles that maybe you haven't encountered yet so far. The x squared tile is a large square filled in, and the negative x squared tile is a large not filled in tile. But maybe you never thought about why these tiles are the way they are. So I want to just put in a little explanation. They build on things that kind of make sense. If you think about it, the x squared tile is really an x tile and another x tile. And think about the area of a square. It's length times width. X times x. X times x is x squared. Okay? It's the same with the other tiles. Take a look. The x tile is really a 1 times x. 1 times x is x. And even think about the 1 tile. What's the dimensions of it? 1 times 1 is 1. So those tiles actually make a little more sense if you think of them from a geometry standpoint. I get that for some of you, that just made things even more confusing. So don't think of them that way. Just memorize them in terms of what they are. Go back to this one and just think about the tiles in that way. You'll be okay. Okay, for others though, maybe you need that little bit of a deeper understanding there. Okay, final thing I wanted to talk about today is this idea of word problems. And I want to introduce another recipe for you guys. How to work through word problems. This one's a little more non-concrete, But let's see if this can work. That's a quote from Einstein. When you're working on word problems, you are essentially taking some real problem in the real world and turning it into math, solving it, and then turning it back into the real world. So for example, you order pizza tonight. You got to tip the driver. How do you do that? You could just guess and grab some money out of your wallet and throw it at the driver until he runs out of the room. But most likely what you're going to have to do is take that real world problem, turn it quickly into something in math, figure it out.
I'm just looking in my pocket.
Okay. Once you got the answer, turn it back into a real world problem and hand the money to the driver. Okay? Basically, again, if you think about it, that's why we call it an expression. You are expressing what you're doing in math. Okay? Okay. So, when you have these sentences, here would be my suggestion for ways to work through a word problem. Step 1, pay attention to clues. Okay? There's going to be clues in the word problem. Step 2, you know it's a math problem. So if anywhere in the word problem, there's a number, chances are you're going to have to use that number. Sometimes the number is written in like an actual 2, and sometimes they'll actually write TWO. But you know that's still a number. So my advice is highlight those. If you're on a test, underline them. There's a number. I bet you that's part of this. Because very often I get students, when they have a word problem in front of them, they just freeze. They don't do anything. Also, watch out for words that indicate operations. Like if you see the words more than or product in the word problem, that's telling you what you should be doing. If you see product, you think, oh, I better be multiplying two things. 4, always focus on the final question. Like, what is this thing actually asking for? Don't solve something else. Solve what it's actually asking for. 5, read it again. Always read a word problem more than once. Make sure you got it. Then 6, finally, now you're ready to jot down what you think it is in actual math. Let's give an example. Jane and her 3 college friends are going to share an apartment. They're going to college, they decided they want to share an apartment. The cost of the rent is $600. What's Jane's share? This is actually a super easy one. But let's go through the steps. Step 1, read the problem, look for clues. It's pretty simple. I think the clues are evident. Step 2, highlight numbers. There are some numbers here that I can know that those are going to be part of the problem. So make sure I highlight them. Step 3, watch for operations. Don't really see any in this one. Step 4, focus on the final question. Make sure you're answering this. Your answer will be Jane's share is. Your answer won't be Jane's friend's favorite color is. Like, no, make sure you focus on the final question. 5, read it again. Make sure you understand. 3 friends sharing means an equal amount. The unknown value is what we're looking for. The unknown is Jane. Jane is what we don't know. Step 6, let's turn it into math. If R is the rent, and we know the rent is $600, and we divide it by the 3 people, and J is Jane, then $200 is what Jane is going to have to spend. It's actually an easy problem, but it's the way you translate it. Yes?
Jane and her 3 friends, wouldn't it be 4 people because the Jane plus the 3, that's 4.
That's right. That's exactly right. You caught it. That's what I was going to say. My next question was, did I make a mistake? And you caught it before I even was able to ask. You're right. Okay? So watch out for those. Very common. Okay? Just those little things that can make a mistake. Now, if you did this, Austin, is there a problem? Do you need something? Can I help you with something? Okay. Then maybe if you could sit down. Watch, if you did this as is and handed it in, you're still going to get points. Making a little mistake like that doesn't mean you get 0. So a lot of these tips, again, are just tips to kind of help along the way. Let's wrap with a couple quick examples. Here's a triangle. Okay, well, here's a triangle. Find the perimeter. Now, this is a weird type question, okay? But what I'm saying here is, if you have the perimeter for a triangle and the perimeter for the square are the same, what's the perimeter, or sorry, what's the length of one side of the square? These are the kinds of problems where it takes regular algebra and all of a sudden makes it super confusing. So let's break it down. Let's work it out. Well, the perimeter of the triangle is all 3 sides added up. And if I take all those and add them up, I could simplify that down to 4x plus 16. Now wait a minute. If the entire perimeter is 4x plus 16, and now I have a square, what's each side going to be? Well, each side's going to be that divided by 4. X plus 4. Okay? Watch it. That was a tricky one. I wanted to throw that one in just as a tricky one. Let's try another one. Last night I went to a movie. My wife later rented the same movie, back in the days when you could rent movies. It cost me 4 times as much to go see the movie as it did for my wife to rent it. If we add the cost of what both of us spent together, we both spent altogether $10. How much did each of us spend? Okay, now hang on. I know you can maybe answer it, but let's work it out. If S is the money that I spent, okay, and R is the money that my wife spent, I know my wife, I spent 4 times as much as my wife, so 4 times what my wife spent equals what I spent, and I can work this out to come up with the answers that I spent $2, and therefore my wife spent $8. Okay? Yes?
Are you going to pull a you made a mistake thing again because your wife was the one who bought it too? False.
What? No, she's the one that rented. No, this one, I didn't make a mistake on that one.
You just said that the wife was one who went to the movie.
No, it doesn't say that. It says I went to a movie. Oh, I may have said that, but the question doesn't say that, okay? Okay. Lake Ontario is 77 kilometers shorter than Lake Erie. The length of the 2 lakes together is 699 kilometers. What's the length of Lake Ontario?
77 kilometers shorter.
That's right. But let's work it out. Okay, again, in your notes, if you take a look, Ontario minus 77 equals Lake Erie. Ontario plus Lake Erie equals 699. Ontario plus Ontario minus 77 equals 699. I can use algebra to solve this. Now, guys, whoa. Shh. I just wanted to show you a couple of these. These are kind of tricky, and there's stuff that you're going to have to practice to get used to. I don't want to go into all the details of all these word problems. I want them just up there as quick examples. We're going to move on, okay? Let's hit the final big deal here. Know your language, okay? Know what the word's asking. I'm not going to go through all these. You should already know what all these are, okay? Second thing, know your methods. 2 methods. The cake or the simplification method, to make it simpler, has 4 steps to it. The inverse operations method has 6 steps to it. I'm not going to go through them again. You know them, or at least you know of them. Those are your things. The third method I introduced today is how to work through word problems. It also has 6 steps to it that might be helpful to you. These are 6 recipes, like I just gave you, 3 recipes I just gave you to help with the unit. Try them, okay? And then last thing is you also have a model for visualization. Okay? All right. Whoop.